Do you hear me? Cool. So let's begin. And first, let me remind you what we were doing last time. The area of semantic technologies can be represented as layered, I don't know, pie, like Napoleon. At the very bottom, we have an alphabet, which can be used, and then a basic language for information exchange, which is XML. And this is what we considered in the first lecture, these two things. And today it will be a little bit more serious. We are going to move to the next level, to relational data, and consider RDF and RDF schema. However, the official computer-oriented language for RDF is based on XML. That is why I spent last time to explain or to remind you what XML is about. I also want us to quickly analyze. We are going to start by quickly analyzing why XML itself isn't suitable as a good semantic technology. Let me quickly show you one application. Oops. Just a second, I have a problem with the sharing. No. Okay, I'll show you then later, because at the moment I can't switch between my iPad and desktop. Okay, so let's move on. No, now it allows me. So no, not really. No, something isn't working. I mean, nothing is working. What do you see on your screens? Do you see the next slide? See this one?
Yes, I can see.
What can you see now?
Like, why not XML? This slide actually.
So you why not XML? This slide.
Yeah.
Interesting. Just a second. Resume share. Just a second. New share. Okay, so. Okay, now you should see my browser. Is it correct?
Yes.
All right. So in the browser, there are a lot of pieces of software which were developed to support XML. And in this particular one, it is an XPath tester or evaluator. I show you a simple XML document here. And let's quickly have a look. XML is about representing information in tree form. So here we have a root, and the root element, well, it's called root. Okay, then underneath we have actors, and singers. right? So these are two children roots. Below actors, we have some concrete actors and so on. You know, this is what XML can do. And we can write queries in XPath, say like this, which wants the machine to find all actor elements which are below actors, which is below root. Yeah, I run the XPath engine and obtain these results. Yeah, the results are here. So the machine finds three answers. Now, this is a query language for navigating through tree-shaped data, if you want. All right, so this is what XML can do. And the question is whether you can represent everything on Earth using XML. So let's return back to the slides. Okay, so we are back to the slides. And my first question is, okay, so does XML provide us with a good language for semantic technologies? Now, on the surface, it gives us some structure, namely tree-shaped structure. For example, suppose I have this information. Michael is the lecturer of the semantic technologies module. All right, how to represent it in, say, in XML? There are many ways. Yeah, for example, I start thinking, okay, what's the most important thing here? Okay, let it be module. Yeah, so I create an element module and collect information underneath. Right, but then you would say that no, the lecturer is more important. Who cares what he talks about? The lecturer is most important. Okay, then we have another element, lecturer, and the name, and then the module. Yeah, or somebody at the university level, no, guys, come on, who cares about lecturers' modules? It's what the university is offering. Yeah, so then it will be something like this, teaching offering. So basically what's happening is that we organize information according to some principle, but we don't deal here with basically any meaning of the tag nesting. Yeah, they are just like an envelope where we collect some data. So how shall we proceed then? Yeah, and if you look, if you consider more complex examples, then you'll see that tree-shaped representation of information isn't adequate, not always adequate. Just imagine that you have structures which are, say, like this, which are not trees. Yeah, and we'll see a lot of these things. Okay, let's now consider seriously how other disciplines, how other sciences represent information like this. Okay, I'll give you a couple of examples. One from AI. And in AI, sentences like I showed you, or here are other examples, have been represented since actually the 1960s, have been represented in the form of labeled graphs. Yeah, something like this. And in AI, these graphs were called semantic networks. Right, and if you look at this particular example, then you see that in this graph we have nodes. They are labeled. Yeah, some are labeled, say, like this black node. It's labeled with a name, and it represents an individual, Eve. Yeah, and there is another individual, Adam, and a relation between them. is represented as a labeled arrow. Yeah, Eve loves Adam. Very, very natural and simple representation. Yeah, we can all draw pictures like this. Now, this one, this node is a little bit different. Yeah, because it's mother. It's not an individual. Yeah, probably it represents a class of individuals. Yeah, a set or a concept in language. And Eve is an instance, yeah, an element in this class. Yeah, so we may say that Eve is a mother. Yeah, and this information, this sentence is represented by this piece of the graph. And so on. Okay, and here, this bit simply says that every male is, male is an element of Homo sapiens, or something like this. Yeah, so what we see in this picture is some individuals, binary relations between them, some classes, and some subset relations between classes. There was it's nearly suitable for semantic technologies. There is one problem, that in semantic networks, the semantics haven't been properly fixed. Yeah, if you start thinking about these representations, then say how to understand this bit. Eve, then parent, going to child. Yeah, probably it's supposed to mean that Eve has a child. Right? That is, there is an element in the class child, or some elements in the class child, whose parent is Eve. Yeah, and the other arrow, this one, is just a subset relation. Or not? No, every child, no, it's even harder. Probably it's supposed to mean that every child has a father. Yeah, so these things needed clarification. Okay, yet it's a very good example because the representation is graphical. Representation consists of nodes. Nodes can be classes or individuals, and binary relations between them. Okay, let's remember this. In grammar, since Aristotle, sentences, all sentences, or nearly all sentences, were divided into two parts. One is called the subject, and another the predicate of the sentence. Yeah, so the subject, this one, is, or it refers to the origin of some action. Yeah, somebody acts. Yeah, Michael is a lecturer. The predicate refers to the remainder of the sentence. Yeah, and the predicate can be true or false, depending on whether what is expressed is true or false. Yeah, Michael is a footballer is false. Michael is a lecturer is true. Okay, predicate, the predicate part is further divided into a proper predicate, which is normally represented by a verb, and an object. Yeah, to where the action goes. Yeah, Michael teaches semantic technologies. Yeah, Michael is the subject, teaches is the predicate, and semantic technologies is the object. Yeah, and every sentence, every statement sentence, every proposition can be represented or divided into these three parts: subject, predicate, and object. Three, which means subject, predicate, object. This is where the action starts, this is kind of the action itself, and this is where the action goes. All right. Now, in mathematics or mathematical logic, yeah, there it's everything is pretty formal, and we have predicates or relations like this. Yeah, loves is the name of this particular relation, and Adam and Eve are kind of arguments, yeah, objects to which the relation applies. Yeah, loves holds true for Adam and Eve. Teaches holds for Michael and semantic technologies, and so on. And here it's simply that MZ is a lecturer. MZ belongs to the class lecturer. So formally, a binary relation is simply a set of pairs. So we can define a binary relation between any two sets, yeah, which can coincide as simply a set of pairs. Yeah, for example, A is, I don't know, people or persons, B is persons, and we select all pairs, person 1, person 2, such that the first loves the second. Yeah, and let me also remind you that the domain of a relation, yeah, is the set of all objects that can appear on the left-hand side, yeah, this X. And the range is what can appear on the right-hand side. Domain and range. Okay. By the way, binary relations are very nice because we can represent them graphically, as I said, simply. Pairs of nodes connected by an arrow. But in principle, in mathematics, we have more complex relations. Yeah? For example, ternary relations, 2 points and a straight line coming through this 2 points, yeah, 3 relations, or from life, or I don't know, a referee in a football game, or actually they have one main referee, 2 linesmen, or maybe 5 linesmen, or whatever. Yeah, so in principle, we may need n error relations on some sets. Yeah, and these relations mathematically are simply sets of n tuples over an appropriate set. And one array or unary relation, yeah, in mathematics, they are called sets or classes. Okay, the same stuff in databases. Yeah, say we want to represent something like this relation, registered for, yeah, a student registered for a module. Okay, so this is a piece of data. This, well, we can represent it as a simple table with 2 columns. One column, say, the students, another column, arrows, and modules, yeah, and pairs like if A, if B will be in the relational table. Graphically, we can represent it like this, yeah. This is clearly a directed graph, yeah, and this is the database representation, just pairs. All right. So this, of course, is well known and easy, and that was the first important step in the RDF definition. Now, RDF stands for, where is it? Resource Description Framework. It's an official standard language for the semantic web and semantic technologies in general. And this is a link to the place where it was formally defined by W3C, by the World Wide Web Consortium. On the surface, everything is very simple. Yeah, it's a trivial language because there are 2 main principles in RDF. Here one, and here is another one. All resources, that is everything which is available on the web or elsewhere, are identified by URIs, yeah, or IRIs. Okay. And second is that we have statements which describe properties of resources by means of simple triples: subject, predicate, and object. That's it, the whole science. Okay, let's go a little bit further. So what can be the subject of a triple, predicate of a triple, and object of a triple? Right, there are some restrictions. Every subject must be a resource identified by a URI. Yeah, say book, but this book must be a URI. Predicate is it's called in RDF property, is also identified by URI. Yeah, say book written by, both of these things must be URIs. And finally, object. For object, that is the value, we can have either a URI or a literal sequence of characters. Yeah, like book written by, I don't know, John as a literal, or John identified by a URI by referring, say, to John's web page. Right, so properties are always URIs, and therefore they are also resources. What happens if I don't want to give a URI, John's URI? What if, or I don't know, I know that a book is written by somebody and I don't know this somebody, or for some security reasons, I don't want to show URI. Well, there are so-called blank nodes that do not identify specific resources. So this thing, blank nodes, is not so transparent as the other, as just a URI or literal. We'll come to this, we'll be discussing this several times. Now, URIs, as you remember from the previous lecture, stands for Universal Resource Identifier. You know all this. There are URIs like this links, HTTP links or hyperlinks, and they can be URNs, yeah, uniform resource names. Yeah, it's not a locator, resource locator, is just a name. What is important is this one. So in RDF, URIs are often given like this. Oh yeah, here is an example. Yeah, so we have a kind of a URI with hash, with this character here, followed by something. Yeah, so what is that? Yeah, this hash is called a fragment identifier. What happens if I click on this link? Okay, let's see what happens. Yeah, we actually come somewhere to, you see, this is the URI. We see the element here, the element fragment of a certain document, Dublin Core Metadata Initiative. And by clicking on that link, I come just to this element fragment of the document. So at this point, probably this is enough for you to know. Yeah, so hash followed by something refers to a fragment of a document. Okay, so how do we represent these triples? Don't forget that in semantic technologies, apart from people, we have computer agents. Yeah, so the language we are aiming at should be understandable by computers. Yeah, so we don't want to have graphic representations read by computers and interpreted in a certain way using, I don't know, machine learning. No, we need some formal languages. So there are different, because of this, there are many ways of representing or encoding RDF triples. So here are 3 of them. One is just like this, just triples as they should be. 3 components, and we have a URI here. Now you see this hash character. This is the subject. Then the second one is the object of this triple, and the third one also URI, and the third one is in quotation marks. This is the literal string of characters. Not just nothing sophisticated. The only problem, of course, with this representation is that there are too many characters. It's very difficult to read. So we'll need some better ways of representing this information. For example, why on earth we should repeat this bit of the URI so many times? Maybe we can denote it by something, introduce a namespace, and don't write it all the time. There will be a language which has triples like this and intended for human consumption, and it's called Turtle. Yeah, today or tomorrow we'll come to this. The second language, the second way of representing these triples is, of course, a directed graph representation. So it is something like this, although I didn't write here the full URIs. Yeah, so we have a directed graph. We have nodes like this or like this, and we have these directed edges represent properties, predicates. In this case, in this example, actually turns out that it's a tree. Yeah, but in principle, it doesn't have to be a tree. It can be a pretty complex directed graph. All right, and the most horrible is the XML representation, XML syntax. So, and this is the kind of official machine-oriented language that is used to represent RDF triples. So what I'm going to do now, I'm going to look together with you, I'm going to look through a few examples and explain how to read and understand these documents. You will never be asked to write such documents because, well, there is some software. We'll be using this software and more or less natural human language, and the machine will translate this language into the XML system syntax itself. All right, let's start reading. So the important thing here is now this. So we have an RDF element, opening tag, closing tag. This one refers to a certain namespace, remember? And this namespace is defined here. XMLNS, namespace, RDF. And RDF refers to this thingy. Right, so whenever in the document we have something with RDF like this, this means that this bit will be replaced by this one. Now, this is how we use namespaces. We just give a URI, possibly with this hash symbol, And after that, we never use this URI explicitly, simply by writing the namespace. Okay. Then next, I have another namespace. I write DCS, Department of Computer Science, and also give a URI. And finally, I also have some base. Base, if I don't write any namespace, say here, MZ, then this MZ should be attached to the base here. So by doing this, we can save our energy and not represent all the ugly URIs. Okay, let's go further. Now, these are not triples. These are namespaces, some definitions of namespaces. All right, now we describe triples. And here is a description element. And it says that what? It's about ST. Yeah, so here we have ST, and it's our node. This is the subject of the first triple. Then is stored by here is the predicate, the property. So is stored by is here. And the object is there. Yeah, so we represent a triple like this. We have a description element. About refers to the subject, the first element of the triple. Then this one, the next element, refers to the property, and this one refers to the object. Then we have another line here, this one. Yeah, it says that the same ST is related by name with a, oh, here is, it's not a URI, it's a literal, so I represent it like this, semantic technologies. Oh, and then there is one more triple with the same subject, it's here. Yeah, there is home page. And it goes to resource, some long URI, this one. Yeah, so this is an XML representation of the graph, the triples in the graph I showed on the right. Then we have another description which describes what? About MZ, that is, this one now is the subject. And the name, so there is a name arrow, and it goes to Michael. So Michael is here. Yeah, that's it. Well, seemingly that's it. There are many other aspects of this representation. Okay, to sum up, an RDF document is a collection of RDF elements. Okay, and these elements describe triples. So these triples are described by description elements, and they are called property elements. Okay, so this description here describes triples with this ST as the beginning, as the subject, and giving property value pairs. Property value, property value. Yeah, same subject, different properties, and corresponding values. All right, now if my document wants to introduce a new resource, yeah, how I can refer to resources? There are two ways. One is this, RDF and then resource. Yeah, for example, like here. Another one is RDF ID. My document may introduce a new resource. For example, here, my document introduces a resource called MZ, which here there is no namespace, so MZ is attached to the base. You remember where the base was? Here is the base. Okay, so in one place, or the document may introduce an ID. In another one, it can already use this as a resource. That's not so important for our exercises, but you should be aware of this. And so RDF ID defines a resource. If you want to know about this, click here. Oops, no, I don't want to open it. Otherwise, just remember that there are two ways of referring to resources. One is RDF resource, another is RDF ID. Of course, you should not introduce a new ID twice. I mean, the same ID twice. It can be introduced only once. Okay. Now, in the XML-based syntax, there can be nested descriptions. For example, what happens here? Let's try to understand. RDF description begins, ends. Yeah, so this is the subject. Okay, so this is ST, the subject. Then we have property, name, value. Semantic technologies. All right, then another property is stored by. Okay, is stored by. Yeah, and this is the beginning, this is the end. Yeah, so what's in between? In between, I introduce a new triple. So this arrow goes to MZ, which is the object of this triple, and the subject of the next triple, subject, predicate, object. You can use this nested structure in order to describe two triples, yeah, where MZ1 is where MZ is the object, and another one where it is the subject. Okay, and now one more important thing. There is a special element which is called the type element. And this element allows us to classify things. For example, what I write here, ST is of type module. Right, so it is something like this, ST. Then this is a special property, RDF type, and here it refers to module. But then this module refers to something special, right? It must be a class. Yeah, there is a, I don't know, mathematical analysis is of type module. Yeah, or machine learning is of type module. So this module is a class. And here is exactly where we have some semantics. Or this is another example, MZ is of type lecturer. Right, so this triple puts MZ into a class. Yeah, the class of all lecturers. Of course, there can be other types. For example, what's here? Yeah, I can write another triple saying that MZ is a taxpayer, or I don't know, football fan, or I don't know, swimmer. All right. So we have triples, and we have some special triples where we define types of certain URIs. Okay, what else do they want us to know? There is some special abbreviated syntax. Yeah, people first invent a formal language, and then they see, and then they look for ways to avoid these strict rules and find shortcuts. Yeah, of course, shortcuts are in every language, and RDF isn't an exception. For example, in when we use RDF type, right? So the notation I introduced on the previous page was like this: ST type module. All right. So instead, I can write like this: description, ST, and then you see here DCS name. Oh, sorry, no, I wanted, no, let me. Yeah, okay, so this is how I defined the syntax on the previous page. Now, the one abbreviation is like this. When I have this type, yeah, I can include this type, the type itself. I can take this type itself and write it in place of description. Yeah, and this is what I'll obtain. DCS module. Yeah, when a description of a triple starts with something different from description, then it will be the type. Okay. This is the first thing, and the second one is using attributes. Yeah, childless property elements can be replaced by XML attributes. For example, what we have here, ST has name semantic technologies, and instead of this, I can write this attribute. Yeah, ST, then name as the property of the triple, and semantic technology as the. So all these three representations are equivalent, and all of them represent just this, the graph shown below. So in principle, your task when I give you a document and ask, draw a graph representation, you just look for these triples, and your task will be to find all the triples, including the types. Yeah, this is type gives a triple, then the attribute gives a triple, and this is taught by also is the property of the third triple here. Okay, so very tricky agreements to represent simple graphs. Now, it's getting a little bit even more harder, because, as I said, in real life, mostly we have binary relations. Yeah, Eve loves Adam. But sometimes we need ternary relations, or n relations in general. For example, I want to represent the following situation. So I want to represent a situation when X is a referee of a chess game between Y and Z. So I have three participants. How to represent this thing? How would we do this in, say, using a picture? All right, so we have X, we have Y, and we have Z. Now, what's a natural way of doing, of representing this? Say, if I just draw like arrows like this, that's definitely not the case. Yeah, it's some information is missing that Y and Z are involved, or all the three of them are involved together in a certain game. So a better way probably would be like this: represent the game with three participants as a special node. Yeah, and then X will be a referee, and this will be, I don't know, player and player. Something like this. Right? And indeed, this is what they use in RDF. So we have, we introduce an anonymous auxiliary resource, this one. Right? And this resource represents the chess game. Right? And it doesn't have any URI. It's a blank node. So I'll be explaining things around blank nodes a few times. So now here is my first attempt. Yeah, if you read here, a blank node, or B node, is a node in an RDF graph representing a resource for which a URI or literal isn't given. Okay, the resource represented by a blank node is called anonymous. And there is one restriction, that a blank node can be either can be used as the subject or object, never as a property. Right? So blank node is really a node in a graph. You can't have a blank node for a property. Why do we need these blank nodes? One use is to represent n relations, but there are other important uses, and I quickly list them here. So mathematically or logically, blank nodes indicate that certain things exist. Yeah, blank nodes indicate the existence of a thing, yeah, without using a URI. It's not that we don't know or the URI is unknown. Yeah, for whatever reasons, the URI isn't given, and that's it. Something exists. So why do we need anonymous resources? To describe multi-component structures. Yeah, like the game of chess with three components. To describe provenance information. Yeah, a document was created by this person, modified by that person, date, and so on. To represent complex attribute without having to name explicitly auxiliary nodes. Yeah, for example, the address of a person. Normally, the address consists of a street, a number, code, city. Yeah, so we collect all this information under a blank node. Yeah, and finally, protection of the inner information. Yeah, so that nobody can query, by querying this document, nobody could get some sensitive information. Yeah, we simply replace some proper URIs with blank nodes. Okay, we'll come to this later. What else I wanted to show you? Okay, so there are a few container elements when we want to group things together. And these container elements are called RDF bag. It's an unsorted container. Or an ordered container sequence. Or a set of alternatives of which one will be chosen. Yeah, for example, in in the game of chess, we have a container. Yeah, this container which consists of two players. Like we have a referee and then a container which contains or comprises Y and Z. We have more sophisticated structures. We have lists, but I'll never use them. So this is a stupid representation of a list as a head and tail. Yeah, I'll never use it, so it's not so important. Now, and this is important. Now, say in social networks, the following type of information is pretty important. Yeah, John says that Bob loves, I don't know, Jane. Right? Bob claims that John loves Jane. Right? So it's a statement about another statement. How to represent this type of information. Say in this example, my example, I say, MZ says that this is the home page for semantic technologies. How to represent this thing? Well, this is, sorry, where is it? Here it is. This is the way how to represent it. Now, MZ says is the predicate of this triple, says S. Here I introduce a blank node, which is of type statement. All right, so I write MZ says S. Yeah, whereas S is some HTTP is the home page. All right, so this is a proper triple. And in this proper triple, I have the subject, predicate, and object. The subject is ST, predicate is homepage, object is. So this is the way of representing statements about statements. So we'll have exercises about this, and we'll see how it is done in different syntaxes. Just remember that if you have statements like this, when somebody claims that somebody said that somebody wanted to marry somebody, then it will be a situation like in this picture. Okay, what else? Now, this is basically what I wanted to tell you about RDF itself. So let's summarize. RDF deals with triples: subject, predicate, object. These elements of triples can be either resources identified by URIs, or in this case, literals. In the case of the third component. And this and that can be blank. Can be blank. And what else? We may have types. Yeah, we may say that this resource belongs to this class. And we know how to represent n-array relations using blank nodes. And we also know how to represent statements about statements. So this is what we have learned so far. Now we go a bit further, and now what's the time? Okay, so we have 20 minutes, and start considering RDF schema. This is where logic shows up. All right, now consider the following RDF document. So what do we have here? Oh, let me draw a picture. So we have already difficult, yeah? Because this is not a description, so it's academic stuff. Right, so this is the class where this one belongs. Okay, so I start with PTW is of type RDF type, and type is ARC stuff, academic stuff. Okay, I write like this, ARC stuff. All right, and there is name, and name is Peter. Yeah, so your typical exercise or task in your test will be like this. Yeah, I give you a document, and you will have to draw a graph representation of this RDF document. Yeah, so this is exactly what I'm doing. All right, then I have another one, and again, this is not description, so it must be a type, and the type is, okay, I'll draw it with, I don't know, green. This will be, type will be professor, prof, and then subject, MZ, is of type professor, and name is Michael. Okay, and what else? ST is a module. Right, let me draw it in purple. Now let it be, say ST here, ST of type module. And it has name, okay, it's name semantic. And what is stored by MZ? So I need another is stored by. Right, you see, so some real life sentences like PTW is an academic staff member whose name is Peter. All right, and MZ is professor whose name is Michael, and semantic ST is a module called Semantic Technologies, and it is stored by MZ. Yeah, so I'll be giving you sentences in English like that, okay, more complex, taken from, I don't know, a book or something, and I'll be asking you to represent the information in these sentences as pictures like this, or as, well, in a better syntax. Okay, but we are not there yet. Now, we have this information. The information is represented in this graph, and I want to find all academic staff members. Okay, all academic staff members, all, what is academic staff in Russian? Преподаватели, yeah? So all prepods. Fine, all prepods, fine, it's easy, yeah? So I have to look for something like this. But here, it's not written that, say, MZ isn't explicitly written that MZ is an academic staff. So some information here is missing. As people, we know that professors are also преподаватели, преподы. So, well, this is exactly what is missing. And this is that somehow should be represented, that the class of professors is a subclass of the class of academic staff. Or differently, you may start thinking that if somebody teaches a course or a module, then this somebody must be an academic staff member, right? So you may say that the range of is taught by is academic staff member, and then the answers to the query, yeah, who are academic staff members, will be PTW and MZ. Yeah, so how to add this information to the documents? Yeah, which for us is pretty natural. We know from experience, and this is done. This kind of extra information about classes or properties, their domains and ranges and so on, is given by RDF schema. Now, when doing this, we are going to face a new type of problems. And these problems will involve reasoning. The reasoning is pretty simple, but it's still reasoning, because the documents do not contain some information explicitly. It is there, implicit, and can be recovered only by applying certain rules. This is where reasoning is. All right, so what do we need exactly? What I want to write is something like this. Say MZ is of type professor. Is one triple, fine. And then I write, as that was my first idea, I just say that professor is a subclass of academic staff. Yeah, so I need a special property, subclass of. It's a new property. It is provided by RDF schema. That is why here it's written RDFS. Okay, we can write this. Yeah, we have two triples, two normal triples. MZ is in relation RDF type with professor. Professor is in relation subclass of with academic staff. Yeah, but something is missing here, right? Because if MZ is here, of type means that MZ is an element of class professor. So class professor is a class prof. Yeah, there can be other elements here. And the second triple says that the class professor is a subclass of academic staff. So AC staff is even larger. Right, from which it takes some calories to deduce that MZ should be of type academic stuff. Yeah, it requires some deduction. So, in fact, I would say that it's not MZ is in relation. MZ is an instance of the class professor. And second statement, there's two, is actually a statement. Every instance of professor is also an instance of academic staff. Every member, element of professor is a member or element of academic staff. Right? So the machine should apply some rules of reasoning, and whenever it has triples like this, it runs whatever, some internal reasoner, and deduces this one. Well, in fact, all logic on Earth basically can be explained in these terms. Okay, sometimes, well, a little bit more complex, but that's it. And we prove theorems where steps of inference like this, the number of such steps is astronomical, and it's difficult to combine the steps into a complex proof. But, well, this is where logic is. So, RDF schema. RDF schema defines a certain schema vocabulary which supports definition of ontologies. And it gives, like in my example, some extra meaning to particular RDF predicates. Yeah? In particular, type, subclass of, we'll see other things like subproperty of, domain, range, and something else. And so RDF schema kind of fixes the semantics. Okay, here is another example. Yeah, is there any implicit knowledge in the following RDF graph? Okay, let me draw it in set theory. So what does it say? It says that, okay, there is a class professor. Why it is a class? How can I see that it's a class? Because it is a subclass of something else, right? So for the computer, there must be a rule saying that if something is a subclass of something else, then the first thingy must be a class. And the second thingy must be a class. All right, it's hidden here. So the computer has to recover this information. Then this class of professor is a subclass, that is a subset of class academic staff. And academic staff is a subclass of simply staff. Okay, so all, I don't know, работники. Right, so this is the extra implicit information. All these three things, professor, academic staff, staff, are classes. The first one is a subclass of the second, and the second is a subclass of the third, and so the first is a subclass of the third. Right, so something like this is missing. Yeah, and we have to indicate that this is class and this is class. We'll learn how to do this. So in order to extract, we don't want to represent this knowledge explicitly. I'll show you in a few minutes, or maybe next time, a graph, some original graph, and the graph when all the implicit knowledge is extracted. It will be huge, trust me. So to do this, we need reasoners. It's a kind of, it's a type of software which uses some rules to extract, to reason, to extract hidden knowledge from what is given. So we have an application, and this application, when we use RDF documents, may need a reasoner to access all implicit knowledge and obtain a full ontology. So RDF reasoners use some entailment rules. And the number of these rules is about 30. So reasoning here is pretty simple. And the rules look like I said. If something is a subclass of something else, then this something is a class, then subclass relation is transitive, and so on and so forth. And so my next task is to, and these rules are supposed to capture the semantics. This is where the semantic technologies are. And the reasoners should be able to extract the semantics. So the next task will be to look through most important elements of the schema language. All right, so we'll start today and continue next time. Okay, so RDF schema, the language. So we have core classes. They are predefined in the schema language, and they have some fixed semantics. So there are some special rules for dealing with these classes. So it's interesting. We have a class of all resources, RDFS resource, the class of all resources. Everything is a resource. We have here RDF class, the class of all classes. I don't know whether you had, maybe in the first year, somebody told you about paradoxes in mathematics. In particular, something about the set of all sets. Do you see anything wrong with this? Have you heard about this thing? Can you? All right, let me say. Suppose I have a set X. Let me denote like this the cardinality of this set. Say the set of all natural numbers. The cardinality, well, we know it's a countable set. And there is a theorem that the cardinality of any set X is strictly smaller than the cardinality of, well, how to write it? The cardinality all subsets of X. You know this. Say we have a set of two elements, and all subsets will be 2, 2, 2 will be 4. So the cardinality is 4. Right. Now, what about the set of all sets? It must have some cardinality. So it must be strictly smaller than the cardinality of all the set of all subsets of the sets. But the set of all subsets must belong to the set of all sets. Something is fishy here. How a set, the cardinality of one set should be strictly smaller than the cardinality of the same set. It's known that this things like set of all sets or class of all classes are pretty dangerous from the logical point of view. They lead to paradoxes. Well, fortunately, in RDF-A, no paradoxes can happen. I'll explain you why later. And second, in real life, this very large sets or classes, like class of all classes, are never used. I just wanted you to be aware of this phenomenon. Okay, we'll come to this later. Now, another class of all literals. Yeah, we want to specify. Why do we need the class of all classes? We want to specify that something is a class, just like this. We don't want to reason about cardinalities. So we have some literals, class of all literals. We have a class of all properties. And we have a class of all statements. Yeah, remember that we need statements, maybe statements about statements. So this is a document which says that, okay, I introduce a class, sorry, I introduce lecturer as of type class. Lecturer is a class. So this will be lecturer of type class. Yeah, so and this one is taught by is of type property. Okay, next. We have core properties. So on the previous page, we had core or basic classes, which are predefined in the schema. Here we have core properties for defining relationship. And one is already given by the RDF language. Note here that we write not RDFS here, but just RDF. The type is already included for whatever reason in RDF. Yeah, and a type, this type declaration says that the resource, which is mentioned there, is declared to be an instance of that class. Okay, another property, another special relationship is this one. RDFS subclass of. Whenever we have such a relationship, whenever we have such a statement, then we have two classes, and one on the left is a class, which is a subclass of the other one on the right. Yeah, so subclass, superclass relationship. And the meaning, the internal semantics is here. All instances of a class are instances of its superclass. We also have this special relationship, sub-property of. This means if you write that P is a sub-property of Q, then we have Q of xy whenever we have P of xy. That is, as soon as we have x related by P to y, the reasoner must add Q here as well. Yeah, here is a simple example, but I'll start with this example next time. So that's it for today. I've introduced the XML syntax of RDF, and I've started talking about the RDF schema, which requires a certain logic reasoning. So we'll continue this next time, and I hope that next time we'll also come to the query language for RDF data. I'll let you know in advance when you are going to have a test. Maybe there'll be just one, maybe there'll be two tests, or there'll be one big test at the end of my 10 lectures. We'll see. It depends on the resources I'm going to have. So I need some helpers to organize this test, to scan your answers, PDF them, and so on. Any questions? Okay, then take care. We'll meet next Thank you for the class. Thank you, guys. Take care.